Hey guys, welcome back to another Science Sunday. I hope the day is treating you well so far. I hope you've had a good week. I have been so busy with painting, it's not even funny. Sam's been working on our truck, so we've been barely sleeping. I'm sure you can tell. I'm wearing my pink puffies and I'm ready to get into it. So today I just was feeling pink today, pink. And so I want to do a pink makeup look, and I figured let's talk about the science of the color pink. Why don't we? So, if the color pink doesn't scientifically exist, why can we see it? Absent from the visible spectrum and neither a wave nor a particle, the color pink is, for many, a scientific enigma. How can a shade that doesn't even appear in the rainbow exist? The answer lies in color theory. Unlike art production, when it comes to eyesight and video production, the primary colors are red, green, and blue. At the back of your eyeball, sitting on the thin, light-sensitive retina, are millions of rods and cones. The rods, all 120 million of them, are all the same, and each is sensitive and only responds to light or its absence. On the other hand, the cones, only 6 to 7 million, come in 3 types: red, green, and blue sensitive. Light is both particle and wave, and like other waves, moves at certain frequencies. The visible light we see zips in at about 400 million times per second, depending on the color. Violet, at one end of the visible spectrum, is the fastest, while red at the other end takes its sweet, sweet time. The other colors in the spectrum moving at their particular frequencies are indigo, blue, green, yellow, and orange. The color pink, not a part of the spectrum, does not have a particular frequency. So I think I'm going to do this a little backwards and actually start with my lips first. Somebody call Barbie. Now, when light from the sun hits an object, all spectrum colors are present. Although typically most are absorbed, the color reflected the most is the color your eye sees. For example, with a banana, every color except yellow is absorbed. When all colors are absorbed, you see black, and when all colors are reflected, you see white. When light gets to the back of your eye, it hits the rods and the cones in low light. A tyranny of the majority occurs, and the far more numerous rods take control of your eyesight. As the rods only detect the presence or absence of light, in this situation, your view looks a lot like night vision goggles. That is cute. However, in brighter light, the cones kick into gear and the world becomes more colorful. The 3 primary colors, RGB, are typically detected by their respective cones, although green perception may also involve the blue and red cones, which helps explain color blindness. When it comes to the other colors, though, it is a bit more complicated. Consider yellow. It exists as a wavelength, but your eye lacks yellow-sensitive cones. In that absence, yellow activates your red and green cones, and firing together, they send a message to your brain. There, your noggin translates the red and green transmissions into yellow. Likewise, blue cones work with green cones to produce a cyan, and with red cones to produce magenta. Sometimes one type of cone is dominant, and a second only partially activates. Oh, shit. Well, I guess we're gonna be purple. This is what happens when y'all don't clean your brushes. Learn from my mistakes. Learn from them. So where were we? Sometimes one type of cone is dominant, and a second only partially activates. For example, violet fully activates blue cones, but only half-heartedly works with red. Both orange and brown, however, have red as the dominant cone type, with green only partially activated. Furthermore, there are colors that require all 3 types of cones. White occurs when all cones fire completely, while black is perceived when no cones are activated. Gray happens when all 3 cone types react, but only partially. Pink, light pink, not magenta, falls into this last category. To be perceived, it needs red cones to fully react and both green and blue cones to only partially activate. Notice, however, how many of these colors, including cyan, brown, and magenta, as well as pink, do not exist on the visible spectrum, yet we perceive them as distinct. It is for this reason that some have opined that color perception is not actually a property of light or of objects that reflect light, but rather it is a sensation that arises within the brain. Ooh, fascinating. Unlike eyesight and video production, art and print production's primary colors are cyan, magenta, and yellow. Why? The difference lies in the fact that the former mixes light, while the latter mixes pigments. So, additive versus subtractive colors. The hues created when the eye, or screen, mixes green, red, and blue inputs are called additive colors. In this process, light waves can be optically mixed by being placed closely together, or by being presented in very rapid succession. In order to work, additive colors require emitted light from a source like the sun or a television. With man-made additive colors, different combinations of red, green, and blue light are fired at a screen. One example might be the vivid red supersuits in the movie The Incredibles. However, not all color we see is the result of addition. Remember that most objects reflect only some light waves and absorb the rest. The colors produced by this reflected light, where part of the visible spectrum has been withheld, are called subtractive colors. For example, the bright hue of a red delicious apple, which has absorbed the blue, orange, and yellow, green, indigo, and violet, is a subtractive color. The primary colors of your childhood remain alive and well in grammar school classrooms, but do not provide as a great range of color. The primary colors of your childhood remain alive and well in grammar school classrooms, but do not provide as great a range of color as CMYK. Each color model's range is limited to its gamut. RGB has the largest gamut of the three and RYB the smallest. RGB, however, which requires emitted light in order to create its full gamut of colors, is unavailable for print or art production. You try to combine green and red to produce yellow. So most professionals and vendors have adopted the next largest gamut available, CMYK. The K stands for black. Lately, pink has come under fire thanks to Henry Reich and his fun, informative Minute Physics. In a 2011 video on YouTube, Reich proves that magenta, which he calls pink, cannot exist, either because it could only exist in space already occupied by radio and gamma rays, among other things, or because magenta is really only the absence of green. Yes, that's what I needed. Just a little bit of pink glitter. In defense of the color, Scientific American's Michael Moyer delved into optical science and noted that given the complicated process of photons and neutrons interacting with our cones and brains, all colors could be considered a trick of the mind. He finished that with, pink is real, or it is not. But it is just as real, or not real, as red, orange, yellow, green, blue, indigo, and violet. Okay, that's all I've got for you guys today. Let me know what you think of the strawberry kiwi look. That's what I'm going to call it. Let me know what you think about the color theory. Let me know what your favorite color is. And let me know what you think I should talk about next week.